Okay. Hello, everyone.
Yeah.
Working?
Yeah.
All right.
Yes. We can start.
Welcome back, everyone. Uh, Today, we're going to do a crash course on Google Earth Engine API and specifically focus on API. I'm Serkan Isik, postdoc at OpenGeoHub, and we will cover some introduction to Google Earth Engine and what is this platform and how we can exploit it, especially in terms of Earth observation data sets and some processes baselines, and how we can install and use API through Colab or in your computers via Python. And also we will cover the types of data sets and structures we have in Google Earth Engine and how we can manipulate those to extract some data from cloud objects. So a lot of people actually beginning to use Google Earth Engine, and actually the number of users is increasing more and more. And the most basic reason is for this. Of course, we are having petabytes of data sets daily from lots of satellite missions, and we're still continuing to launch more. And these data sets cannot be handled in local computers quite easily. So we need a cloud access where we can actually store these huge data sets. And also, if we can do some competitions with these data sets, that's actually a quite computing power that we usually rarely achieve in local machines. If you don't have any high performance computing systems or any other high computing power, usually we don't have access to these sort of huge data sets and have a chance to play with long-term data sets, maybe in a global or regional coverage. So Google Earth Engine actually enables this sort of computation quite easily. But of course, it's not the only platform that we can do this sort of computations. There's also a planetary computer run by Microsoft and Amazon Web Services. I'm sure you've heard a couple more. So these platforms are also getting more and more into this. So we have an option to play around in these services, and most of these cloud computing services have the most basic satellite information usually stored in them. Yeah, I mean, basically, I'm talking about Landsat and Satellite or Copernicus services, of course, because these are usually the at least 90% of the Earth observation data sets are actually derived by these satellite constellations, because they are both huge constellations, also high resolution, high to medium resolution, we can say. So most of these cloud computing systems have these basic Earth observation archives in them, so we can easily play with them. So a planetary scale platform, Earth science data and analysis. So actually, these cloud-based platforms, like we said, have petabytes of satellite data already installed in their archive called data catalog, usually. And Earth Engine also has a specific data catalog that we can filter based on certain keywords or certain catalogs, so we can easily find whichever data set we are looking for. And they also have some contribute some community catalogs in their system, which means the data sets are not only run by Copernicus or NASA sort of high services, but also people like us can also contribute to those catalogs if we calculate some sort of a data set that can be applied to a certain region or in a global extent, and we would like to have the users to be able to access them easily. We can also submit a data set with, of course, certain criteria. So usually when we talk about Google Earth Engine, the first actually interface, the user interface that comes into my mind is the code editor that is already pre-built within their system. So when you go to Earth Engine web surface, when you try to play with the data set or try to open a code, you are directly being redirected to the code editor. So in this code editor is actually quite convenient to use, actually. We have a couple of basics in this interface. You have on the left a data search engine, and also at the bottom you have your scripts that are already saved or pre-built in the Google Earth system, so you can directly run them. And also in the middle, you have the JavaScript coding node, where you can actually write your own code or manipulate what is already written. And on the right side, you have tasks inspectors, which the things you see when you run your code as an output, like objects or tasks that are being run or completed. You can also see the list of them on that side. And at the bottom, we have a map, interactive map, where you can see the pre-built satellite images, but with the images that you already run in the analysis, if you, of course, ran properly, you can see them visualized on top of the surface or terrain. So we talked about data catalog, and when you go to the data catalog, you see different categories and tags, and some certain catalogs that are already created outside this all data sets platform, like Landsat, MODIS, Sentinel. Like I said, these are quite a major data sets that are usually used for most of the Earth observation cases. So that's why they are already have their own sections when you go them. You can if you go to Landsat, MODIS, or Sentinel, you will already see some sort of categorization based on the level of data or pre-processing steps or some sort of examples based on created based on these catalogs. For example, let's try to go to data sets in the Earth Engine catalog. So if you open the Earth Engine catalog, you will see something similar. Already see some themes that you can search for: temperature, climate, weather, or atmospheric. Or if you go to Sentinel, for instance, we can see all the Copernicus missions that are already available in Google Earth Engine. So let's try to check Sentinel-2. And in Sentinel-2, you will see different level of processing, level 1C, which is top of atmosphere reflectance, and the surface reflectance, which is level 2A, which means they are actually bottom of the atmosphere reflectance. And if you click on one of the catalog, you will see all the metadata information, when they're actually available, which time span they cover, the band information, and all these metadata that you should be carefully look before you start processing for them, is actually available here. Usually, the most important metadata that we search for data in the catalog is usually their resolution, their scale, and their time span. So when you search for a data set, but maybe you don't know what you're searching for, we usually go for what kind of resolution, what type of resolutions we have available in the data catalog. So you can see also all that information in here, the band and image properties and the description. For instance, for different bands, we have different scale. I'm sure you are all familiar with the spatial resolution of Sentinel-2, but let's assume that you open X data that you're not familiar with. Or sometimes data catalog has different version of the same data set. For instance, you may have the same climate data, but processed in a different spatial resolution. It's usually the case for instance, ERA 5 sort of climate models. They also have some different versions that are assimilated with other data sets to have higher resolution versions. So when you just look for instance, ERA 5 model, you don't only get 27 kilometer resolution, which is the native resolution of ERA 5, but you may also have different downscale versions. So when you're actually running analysis on these, you may need to remember the name of the catalog that you run in your code, because based on small changes in the name, you may end up with a different catalog in your process, and that could introduce also error unintentionally. So we may have to remember that. So there are different data sets that covers, of course, different level of details, and also different topics in the Earth, like biosphere or ionosphere, troposphere. And so there are lots of variety data sets that covers different parts of the biosphere, and also human factors as well. So people can not only access these data sets to do some processing, but also you can also create some web applications only for visualization, or do some simple computations. For example, you can load some layers and do on-the-fly slope analysis, a trend analysis using a time series of a certain layer, or you may have a data set that you can play around with some certain coefficients, and you can see the effects of different parameters on the results. So it's also possible to do this sort of web applications that user can also interact with the data easily. That's why it's actually in the first part there was this motto of Google Earth Engine: satellite imagery plus your algorithm is equal to real-world applications. So you can create real-world applications using all these systems easily. So of course, there are some data structures when you are writing code in Google Earth Engine. For instance, we have images and image collections, which are completely different terminology in the Google Earth Engine. So if you have a single image, of course, without any temporal information, that is called image. But if you have at temporal periods or different layers in a certain collection where you collect multiple images, then it's called collection. This difference actually important because of the different functions that we can apply to image and collections, because certain functions can only be mapped onto collections, and some certain functions can only be applied on the image itself. So, and not all of the functions can be applied to all of the data set types in the Google Earth Engine. So when we check for the user guide, if you find a function that works for you, that may not work for a single image, that may be suitable only for the collection itself. So you may have to treat carefully in that case. Of course, we also, other than images, we have some basic features that we usually create for some basic vector information, like point or buffer around the point, some polygons that we created for representing the region of interest, per se. And these sort of vectoral data sets are called features, which are geometric objects. And they are usually collected under Earth Engine feature module, which we will see in a minute. So, for instance, this data set is a sort of example of an image. The SRTM digital elevation model. This is actually static digital terrain model, which means it's only collected once, and there's only one band and one single time frame, which is collected, which is now available as Earth Engine.image. So when you go to data catalog and click one of the data set, at the bottom, actually, you can see in here, Earth Engine snippet part. This is actually the code to access that image or image collection. And if it's a image, it's only available for a single band or a single time. So from the dataset availability, you can also see that the temporal resolution is actually for only one temporal stamp. Of course, Sentinel-2 MSI is an example of image collection. So when we see the dataset availability, we see that it's available from 2017 up to now. And from the Earth SNP, we can see that it's labeled as image collection. So when we call them in the code editor, we are actually trying to call them using the image collection function. So, of course, this interface is completely on the web-based, and you can only code in JavaScript. And today we will cover the hands-on with Python examples, and for which we cannot use the web interface. From some time ago, I remember Microsoft Planetary was actually using Python also as an available language in the web-based part, but it's been some time since they also shut down that feature. So you cannot run a Python API on the web application part also. And I'm not sure about ADS. I've never experienced that, so I don't know that part. But it seems like there is no Python API sort of interface on the web part, so to speak. So if you want to use the API itself, you need to use your local machine, or use, if you don't want to install, of course, you can also use Colab sort of environments to run the API easily. Of course, a lot of people uses Conda, which is a nice package to distribute Python packages. So if you're using Conda, I recommend you to create a virtual new environment specific to Earth Engine, so that it may not conflict with the other packages you have. Especially don't recommend you to install it on the base environment. But if you're using any other platforms, you can directly type pip install Earth Engine API, and you can install it. Of course, Earth Engine has also an authentication constraints when you are trying to connect the API, like most of the API services, of course. But to do so, you need to register on the Google Earth Engine. In a little while ago, they also connected the Google Earth Engine part with the Google Cloud projects. So that's why now it's mandatory to have a project name specifically registered for this, so that you can use that project name like you see in the EE initialize. When we try to initialize the API, we need to specify the project name by typing project equals the project name you created. Before that, we were able to do it without creating any project, but since now it's tied with cloud, this is actually a compulsory, otherwise you get an error. Of course, there are lots of training materials on the internet as well, but I must say most of the training materials are actually confusing to separate sometimes whether is it for JavaScript or Python, and people sometimes don't mention what those functions are written for. And to some extent, the syntax can be confusing to distinguish which one is it. JavaScript or Python, but there are of course some certain basics that you can catch, whether if that tutorial is for JavaScript or Python, so you may actually grasp that easily. I think the most obvious one is if you look for a comment sign. That's the most distinguishing part, of course, but for most of the case, you may not see a lot of differences in the function as well. Of course, in the way we map the function to the collection is almost similar, so it can be quite confusing. Also, there are some community-driven contributions for the API as well, and I think GE map from Professor Kushan Wu is the most used and the most famous one that I would say, and he has some extensive tutorials on this as well. But the most important contribution of this package is it can wrap some of the functions that Google Earth Engine gives you and combine with Pandas sort of packages to easily extract some data frame information or easily visualize your layers with volume, which is also a nice extension, I would say. Otherwise, you can also install your own volume map to create some interactive maps. But in GE map, this is already included, so you can also play with GE map to have some interactive maps with your own data sets. So let's switch to hands-on tutorial, which you can also access with this link if you'd like to run for yourself. And so, is there anyone who has no project or any registration to Google Earth Engine? You just did it. Okay, great. I think it's fairly easy to connect those two, and it's just ask a couple of questions about the way you use or you intended to use Google Earth Engine, and after that you can easily create a project, which we need that project name to run this script, of course. Sure. You can actually access these slides in the MetaMorph, and at the bottom you can click this one and create a copy for yourself, of course, because it's for you, it's read only. So you need to create a copy to run the Jupyter notebook. So let's wait if everyone has an access or not. And in this notebook, we also have in the first part, we also have the installation codes with trying accept concepts. So if you download this Jupyter in your notebook, if you already have, you can just skip it without installing either Earth Engine or GE map. But there's a chance that you may not install the GE map, even though if you use Earth Engine. So it's good to have both. So after I ran the first part, mine is already installed, of course, but when you run, it will just a quick installation. But maybe Earth Engine is already pre-installed in the newest version of Colab. I'm not sure because I didn't see any installation, so that could be also the case. I don't remember. But in the second cell, where we have Earth Engine initialize code, you need to change the project name EE to your your project name that you already created under Google Cloud. And of course, the second cell is quite straightforward way to run in local machines. But for example, when I run also, it will ask some credentials, and Earth Engine would like to access to my account, which I have to give, in this case, of course, to the third-party access to be able to authenticate. So on the Colab side, you can get this error when you first run it because it requires the authentication. If you run the second time, since you already authenticate, it will run smoothly. But usually in the local machines, when you have local credentials already, you don't suffer this issue actually. So of course, depending on, I also wanted to print out the versions that right now we installed and we are working for, because also on Earth Engine side and on the GE map side, there are some distinct changes along the way. So when you are looking for a user guide or some tutorial, be careful about which version of GE map or Earth Engine they are using, and there are some strict differences in the functions. So you may need to modify the code drastically depending on the version. So since GE map is already pre-built and compiled with Folium, you can instantly create an interactive map just by typing ge.map with as location information that you would like to center in the interactive map. So I wanted to try Amsterdam, so that's why it's the locations are latitude, longitude, and latitude information is based on Amsterdam. So when you type the map variable, you can directly visualize the interactive map on a notebook. I think we can all run this part, right? Mm-hmm. Is there anyone who received an error up until?
I have to find my project. I don't know where, but you can go on.
Okay, we can. No. All right, we can see our project from here as well. So if we go to Earth Engine to platform, and from here to code editor, on the right side you can see the project name here. For instance, for me it's EE-my name. But also it asks you how to rename it. So if you rename it, you can directly access the information from here. So there's also an important concept in Earth Engine, which is filtering. So when we play with Earth image collections, we are playing the global extent of this image usually. So image collection. So and when we try to access any information in this image collection, if you try to get information without doing any filtering, that will be quite a heavy information to process on the Earth Engine side. So to make it go fast and easily access the information that we need on a local scale or a regional scale, we need to do some sort of filtering to let Google Earth Engine know that we are only interested in certain time range, certain time span, or certain region in the world, or some certain constraints in the satellite, or some conditions in the atmosphere. So we have different filters type, and there are lots of different filters you can manually create. For instance, the first one is filtering by date. So the function is called .filterDate. For instance, if you create if you call an image collection like this, the S2 will cover the whole Sentinel-2 collection from the start to the end globally. So this is actually a huge data set. So if you only interested in certain region, let's say 2021 in June, this will constrain the data set a lot. We can check the number of size the number of images that we actually have in the filtered version of the data set. But I don't want to run this comment in this version because it's still a huge data set. Imagine only 1 month of period for the whole globe. Still, we have lots of imagery. So it will be heavy information to process. So let's try to constrain this filtering by location. Again, we can enter the latitude and longitude information of the region of interest. I'm still using Amsterdam location, but in this case, the longitude and latitude order changes. So please be careful about it. In Google Earth Engine, longitude is every time first, and the latitude is the second information. And for regional bounding, I use filter bounds, which bounds the image collection to a certain region of interest. So I'm creating a first region of interest with geometry.point and entering longitude and latitude, and then filtering the Sentinel-2 collection based on this region of interest. So in this case, we have 1,194 image. So it's still, the number of image is still actually a lot. So we can filter based on cloudiness of this image. Since it's optical image, it will suffer drastically from the cloud cover. So we may have some constraint about the cloud coverage. For example, if you type EE filter, which means EE filter is actually for creating a user-defined filters. So it's not like filter bound or filter dates, which are pre-built filter function. If you want to create a filter based on a property that is already inside in the image collection, you need to use EE filter. So in the EE filter, we are saying that choose the cloud pixel percentage property of every image, and it should be little than, LT is equal to little than 40. If it's below than 40%, the collections will be filters. So in this case, when we run the comment, now the number of images in the collection is 361.
So now the percentage is one of the properties which is already predefined.
That's true, yes. And now we'll see what sort of other properties we can actually have, because this name, cloud pixel percentage, is quite specific and it may not be applicable to other collections too. So we may need to check for each image collection what sort of properties we can actually play with and do some filterings. And we can actually look into this information easily. And before that, I will show how we can actually combine chaining. We call this chaining functions. So you can actually apply filtering date and filtering bounds sequentially without doing any additional assignment in the Python. So you can directly continue typing dot filter date, dot filter bounds, and it will automatically filter on top of it. So you can just do it in one line without doing any other assignments. So this metadata information is quite important to check. So for that, in Python side, I will just take the first image from this collection, and I can do it by typing sentinel2.first, which gives me the first image in this collection that is already been filtered, by the way. And I will check the property information by typing getinfo. This getinfo function is actually to extract the information that is already encrypted in the image part. But if you are dealing with a large data set, large image collections, it's usually not recommended to do getinfo because it's quite a heavy function. So now in our collection we have like 5 images. That's why it's quite easy to implement. But we have some available properties: data take identifier, AOT, retrieval accuracy, and from some of them we will not be even be familiar with the property or don't know what it means. In Python side, you can check these image properties like this, but you can also directly check on the catalog itself. You can go to image properties in the catalog without going into Python side, by the way. So in here, you can see all the image properties that you can select in the filtering part. Some of them make sense to others actually, because some properties is unique for certain applications or so. So from this information, you can check which variable is actually equal to cloud coverage, and you can directly take that function, and you can also see the type of the variable, so you can type in the proper value, of course. So from this, what I can see, there's also incidence angle information, platform selection, which means since Sentinel-2 includes Sentinel-2A and B, you can also filter only for A or for B, which may be also important if you're, I don't know, doing some specific application. Angle also could actually be quite applicable, especially if any of you, I don't know, any of you work with radar images at some point. Yeah, in radar images, the zenith angle is extremely important. The incidence angle is quite important property, because depending on the angle, the backscatter changes drastically. So in this case, you may need to filter for a specific angle, or even usually for specific orbital track, and so that you always have the same orbital geometric configuration in the image collection. That could also be a property that you may need to be careful.
So in any case, I don't have all the properties. Is there any way to filter it out?
What do you mean by all property?
I don't need all the stuff, whatever is being shown right now.
If you don't filter them, you don't actually have to deal with any of them actually. You need to know these properties only if you want to do some specific filtering. Otherwise, you get all of the images that actually has these sort of properties and has different conditions. So when you just call the collection like this, for instance, you get the whole collection without filtering anything. All the certain conditions are actually inside this collection. But like I said, it's a huge data set to work on. So whatever you do on top of this unfiltered collection, it will be extremely slow. So for that, you may need to be careful about. So, for instance, let's try to check the cloud percentage of this first image that we collected. The acquisition date is encrypted as this is actually quite uniform. The system time start is always the acquisition date in all the images. So when you try to also get the acquisition date information along with the pixel or image information, you also need to get system time start, and the cloud coverage is 26% for this image. So that's why it's actually is inside of filtering. So because we try to select below 40, which actually works. So let's try to access the Sentinel-2 image collection with a bit advanced cloud filtering. So even though we try to filter to create a filter at a certain threshold for cloud coverage, the clouds are still there. So for example, in the first image we have 26% cloudiness, so we cannot work with these clouds. We need to mask them out. So that's why in Sentinel-2 and the other collections as well have some may have some certain bands that gives you the indication of which pixels are actually cloud and which pixels are valid pixels. So for that, in Sentinel-2 collection, there's actually two information. The first one is CSL, which is scene classification layer. and the other one is a quality bit mask. So we can use both of them. In the scene classification layer, there's also on-the-fly classification for the for what is already collected from the Sentinel-2 imagery, and there are some certain values that corresponds to different land cover types. For example, 0, no data. 1 is saturated or defected pixels, and 3 is cloud shadow. So I actually need this information to filter out the clouds. And 8, I can see that the cloud medium probability, this is also what I need in this layer. And 9, high probability cloud. And 10 is thin cirrus clouds, which is also another cloud layer that we would like to filter out. So for that, we can write a small function that works on an image level, not on the image collection level, by the way. So for every image, this function does select the scene classification layer and try to access 3, 8, and 9, and 10 pixels, so that we can filter out these classes from the image and label as no data. So this function should be applied or as we say, mapped onto the collection to be applied on each image inside the collection that we already filters. So for instance, let's try to filter again. But now we switch to 20% cloud pixel percentage. And to be able to map this cloud removal function, we are typing s2.map. We need to map this function on the image collection, and we are typing the function name inside, mask s2 sr, for example. So in this case, this filtered collection runs this function for each image that is already filtered and removes all the collection, removes all the cloud information or cloud shadow information. So for visualization, I also added some visualization parameters for RGB images for the natural image. For Sentinel-2, as we all know, the RGB bands are 432. So I will select band 4, band 3, and band 2. And if you run this analysis, you will see 2 images in here. The one is labeled as first image, and the second is the median. So as you see in this part, from the all masked image collection, we also calculated the median value of the whole collection in that certain period, which was 1 month of period. And you can see in this image, we don't see any cloud information, which means after the cloud removal, when we take the median, of course, the number of missing pixels reduces, since we are actually filling with the time series information. But if you want to check the images one by one, for example, this is the first image in the collection. Of course, this image is continuing in the outside the region of interest. Since we do clipping here, we are also clipping the extension of the image, but this image is the part of the whole scene. So you can see all these white pixels that corresponds to cloud coverage. And now in the median composite, we don't see any of these cloud cover at all. So even after we remove the pixels, taking a median or mean or a certain period of data would help you create a composite that you can work better in your application. So, like I said, you can get all the information you want from the get info just by typing S2 size, so to check how many image actually we have. And also, if you would like to access these images one by one, or you may need to download from the other platforms as well, so you can you can see the available IDs of the images for that filtered image collection. And if you go to Sci-Hub or Copernicus data ecosystem, you can actually access the image with the same name that you see here. So this is directly the Sentinel-2 image data set that you can download from these platforms if you want to access the raw image directly. And if you don't want to play in the Google Earth Engine or you need that locally, you can access using these ID. And this is, as you can see, the first part is the acquisition date, the other part is the processing date, and the last part is the military grid system for UTM. For UTM zones and grids, we have some certain specific names, if you'll know. And you can access this tiling information from the Sentinel-2 images, by the way. So the last part is directly the tile name, tile name that corresponds to military grid system. That's why if you want to access a certain region with the UTM information, you can also filter them by the tiling ID also. I think we have a question.
Oh, that was my question. Like, how do you identify the each moving the grid?
All right. You asked how to identify the tiling. Yeah, how that in order to identify the tile or which region the image actually belongs, we can see from this ID at the last part. This code actually corresponds to military grid system, so we can directly access this information. Of course. If you want to get the first image, we said, yeah, you can directly type the first and get the first one, but you can also use the index classically defined in the Python to access the second, third, or the nth number of images that if you want to sequentially access them. Of course, to do that, you need to convert this collection to list first, which we have an inbuilt function to list. And from that you get a list of images that you can play with the indexes. Please remember that the Python index starts from 0. So when we type 1, we access the second image, not the first one. So yeah, when we run this cell. Also in the available layer, you can see that we have now a second image as well. So let's try to close these parts and let's see. I think it's, yeah, okay. It's in the bottom of the region of interest. So maybe we can zoom out a little to see the extent of the image. Yeah, this was the first image in the collection. And this is the second image. Also, you can see the clouds and also the cloud shadows clearly in here. So if you go to the media and composites, you can see that both cloud and also the cloud shadows are also now filtered out. So it's actually better to have a certain time frame to remove these artifacts. So let's try to calculate a vegetation index from this filtered image. We already have a median of this 1 month frame. So you can either write a new function with defining the mathematical formula of NDVI, or there's already normalized difference function pre-built in the Google Earth Engine, so you can also use that. For that, you need to specify with which two bands you would like to calculate the normalized difference with, because NDVI is the specific case of normalized difference vegetation function, which is specific to red and near infrared bands, but you can also create normal combination of bands. So that's why you need to specifically give the band number and you need to know which band number actually corresponds to which one in that collection. And that information is already available in the data catalog that we already seen. In here, if you go to bands, you can see in which wavelength the band name corresponds. And also this, from the description, you can check the band name, because if you go to other sensors, you will find that these band names actually varies drastically. So there is no standard for these sort of things. So let's calculate the NDVI. Of course, we are constraining the whole constellation in a small part of Amsterdam, so that's why the process is quite fast. But if you try to do it in a regional extent, you may not see that sort of speed in your analysis. And with visualization parameter, you can also see. Let's try to zoom in a bit, but it may be a bit heavy to zoom in, because the more we go, the more data sets we are extracting from the Google Earth Engine part, because Google Earth Engine also has some different overviews. So it lets you browse smoothly when you are in the actually lower scale. So which means you can easily play around in the map, but when you try to zoom in, you are accessing the more detailed information, and in that case, it tries to extract the data on the fly, which is why you may have some speeding issues. But in the higher resolution, we can clearly see the changes in the NDVI in some certain agricultural areas, which means it actually works properly. And let's say that we want to access the pixel level information from this NDVI dataset we just calculated. And for that, we can use a certain point, which is in the center of this region of interest, by the way. So you can access this information using reducers. So there are also, after filtering, the second thing, also quite important to know, is reducing functions. We have sampling, reducing regions, and reducers that are pre-built with some basic statistical information like first or maximum, mean, median, or standard deviation sort of reducers. So these reducers, again, work like a function that are already pre-built, and we are mapping these pre-built reducers onto the image to extract the pixel level information. So in here, I would like to get the NDVI value from the NDVI layer I calculated by typing reduce region. And in here, I need to specify the type of reducer I'm interested, which for that, I want to access directly the pixel level information, the pixel value. That's why I can use first. Or if I would like to access mean of the pixels, I can type mean. The geometry defines for which pixels I'm trying to achieve. And for that, you need to give the point information so that Google Earth Engine overlays the point with the image to extract the right pixel location. And also scale. Scale is also quite important. Since Sentinel-2 is actually in 10-meter resolution, I'm typing scale equals 10. If you increase this resolution, you will speed up, of course, but you will not get directly the 10-meter pixel level value, but you will achieve an aggregated value of the of this NDVI layer. That's why if you want high resolution, you need to type scale equal whatever the scale value is. If you write something higher than this, it needs to do downscaling on the fly, and also this will also create slowing down in the code, by the way.
So this is kind of summarization.
That's true, yeah. To directly get whatever the analysis you've done and try to get the pixel value. Also, you can use GE-map to visualize where this point is actually located. So let's zoom out a bit. So it's near here, as you see. So the value that we get, 0.25 NDVI value, is somewhere here that we can see on the map. So the integration of this volume map is quite handy to check whether we are actually correctly running the analysis or not also. So if you want to achieve some zonal statistics like this we talk about, like mean or any other statistics, you can use instead of first, you can type mean, for instance. And for that, if you run on a 10-meter scale, it averages the pixel value in that region. So when you also try to implement a standard deviation or other properties, it will do the analysis on 10-meter level. So again, if you need to aggregate to higher level, let's say 250-meter or 1 kilometer resolution, for instance, you need to change the scale to speed up the analysis. Of course, our region is quite small, so we don't hit the maximum pixel value, but there's a default threshold for the maximum pixels that Google Earth Engine allows you to do this sort of statistical zonal analysis. So if you want to have more pixels, you need to increase this pixels, otherwise you will get an error saying that the maximum bounds of pixel size is achieved, so it cannot compute. Otherwise, you need to manipulate this information. Okay, I calculated this NDVI value, but I would like to access this layer locally. Maybe I will overlay with other layers on my QGIS or ArcGIS, or I will download it and distribute it to others. So for that, we may need to extract this layer as one of the data formats that should work for us. So for that, for example, we can directly export this NDVI layer as GeoTIFF to Google Drive, which is quite an easy work. We need to describe the name of the layer and also the folder to export in the Google Drive. And in the first part of the code, when we do initializing, we already gave an access to our Google Drive. So Google Earth Engine has a write and read access to Google Drive, and it can export this layer as GeoTIFF there easily. Of course, I commented out task start to write it, even though we have a small patch in the Amsterdam. We are still working in 10-meter resolution. So if you try to export it, I guess it should take about 15 or 20 minutes to export per se. But if you change the scale to 250-meter or lower resolution, you can easily, instantaneously get the export on the Google Drive. Otherwise, you need to wait a bit. And let's try to run it. And when we run it, we can see the status of the task by typing task.status. So now it says state running, so which means the competition is still going on, and it gives us the other information about these tasks. For example, I run again, and now it says it's completed. So because now we aggregated in 250-meter level, which is the 0.5 times less than the pixels we had in the original scale, it's quite easy to export, of course. But again, if you do it in higher scales, you need to wait. Also, maximum pixel constraints also valid for the export as well. So if you have a higher number of pixels, you need to play with the maximum pixel value in the export. There is also another way to more easily download this layer. And for that, you can directly get a download. If you have a large amount of data set to export or continuous task process, and we have a task that we are exporting on the loop, there's also CRS information that you can actually play with. And so by default, the CRS is always 4326, which is the latitude longitude projection of the WGS 84 ellipsoid. So if you want to use any other EPGS code, you can also play with this feature easily. So I also provided another function which is a bit longer than what we already have seen. So if you run this code, what it does is it tries to filter the Sentinel-2 between 2020 and 2020 at the end of 2021. So which means you have a 2 years of temporal time span you can work with. And we are trying to reduce the NDVI value in a scale of points. So in here, you can see that our function sample NDVI has a reducer inside with a reduced region function, which takes the mean value of the image based on the point. So which means we are trying to achieve the point information on a scale of 10. And you can visualize the time series of that point for NDVI quite easily because in the last step we converted the whole time series into data frame. So now we have both date time information and also the NDVI value that corresponds to that date time, and the rest is classical Python code to visualize it. And now we have a proper time series to work on. Also, you can export. You can export the table to the Google Drive part as well, by the way. So after you get this data frame information with daytime and the pixel value, if you don't want to have the NDVI as intuitive, but as a tabular format per se, you can use export table instead of export image, which actually works similar way. You just need to specify the export folder and also the export name. You have GeoJSON and also CSV options available for the file format. So if you want directly a JSON file, you can also specify, but you can also export in CSV. Be careful about exporting to CSV if you have a big collection of points and time series, then the file size could be much bigger than GeoJSON. So it's actually, if you have proper set to read GeoJSON file, I would suggest to export in a GeoJSON format. We can extract the same data set from the MODIS also, which is also an optical satellite, but in a coarser resolution, of course, compared to Sentinel-2. So let's first check this collection and see what it is. So if you type the collection name, you can easily find the information on this data set. So this is not raw MODIS data set. So it's already analysis ready data set that is built on top of raw MODIS data. Vegetation indices per 16-day global 250 meter, also downscaled version of this image, and the pixel size is 250 meter. And there is also, of course, different way to bitmask the quality information. If you remember from the Sentinel-2, there was also another quality information, so you can also filter based on this information.
Property also, right?
Actually, we also use the bitmask there. So let me go back to that function.
We use 3 values too.
Yeah, that's true.
What is exactly the difference between these two?
Yeah, actually, the quality layer is directly from this sensor that is actually built before the scene classification layer. Scene classification layer in the Sentinel-2 is also another level of processing that was done after the image is collected and the quality information also was used. And there is sort of on the fly land classification of each pixel, saying that this pixel is actually water, this is land, this is vegetation, or this is cloud or not. That scene also used the bit mask information to mask the cloud information, of course, but in different processing steps, for example L1C or in the lower scale, we may not be able to achieve or access scene classification layer. So in that case, if this function actually works quite clever, if the collection contains scene classification layer, it uses this information, but otherwise it directly goes to quality bit mask. In the quality bit mask, the cloud information is decrypted as bit values. So for that, we have another set of rules that we need to work with, like in here, as explained, for which bit value we need to be careful about for the cloud or other pixels. So this is already pre-built in here. If you extend this bit mask information of Sentinel-2, it says from 0 to 2, 0 to 9 unused, 10 is opaque clouds, and 11 is cirrus clouds. So we have another sort of preliminary scene classification layer that includes the cloud information for the pixel cloud. Yes, it comes with from the sensor directly. So when we download the satellite information, we also have this quality layer in the first level processing. So if we go back to replicating the same analysis with MODIS, so let's. Oh, okay. I think I ran the same part. Yes. Okay. After export, we ran the MODIS part, and at the bottom, now we will try to plot both Sentinel-2 and MODIS at the same time. And this is the comparison of the two time series. Of course, this is a bit expected since MODIS has lower resolution compared to Sentinel-2. And we actually selected a region that is majorly dominated with also the urban features. So when you aggregate the vegetation information in a 250-meter level, of course, we are losing the vegetation signature drastically. So in this two time series, you can see that the MODIS cannot catch the proper vegetation dynamic in this time series, but Sentinel-2 in 10 meter, it was able to grasp that part. Of course, we can also replicate. We can also replicate the EVI, since this information is EVI, by the way. There's also NVDVI. So okay. So in here you see we have NDVI and EVI bands in this collection. Also, we can, instead of EVI, we could have picked NDVI in here as a band, so that it can be both comparable. But since EVI and NDVI both actually resonates in the same scale, they were actually quite comparable. So you can also change to NDVI to make them both comparable. I will also replace. I think we replaced all of them. Yeah. Okay. In here, pattern is a bit actually more similar now, but still you can see that MODIS underestimates the pixel, the NDVI value around the region of interest, of course. So yeah, that's the case. Since EVI is not normalized difference, you may need to calculate, create a new function to calculate the EVI using its own formula. For that, it's also quite easy. Not we don't need to. Okay. We don't need to use any pre-built information per se, but the AVI information is, as you remember, it's quite a linear equation with some multipliers with red band, blue band, and also near-infrared band. So there's one additional band, of course. Since we are able to grasp any band information, you can create a small function like we did in the cloud scaling, cloud masking, and write that formula, and also again map on top of collection to easily achieve any indices we want, not just of course for EVI, but we can create for any other as well. So let's try to access the pixel information in a collectively now. So instead of 1 point, now I listed 4 points from the region. So these are the coordinates, central coordinates of different cities: Amsterdam, Utrecht, Leiden, and Haarlem. So instead of EE geometry point, now we need to create a feature collection. Now, instead of just a simple one feature, we have a collection of feature from the points. So you can easily create the feature collection using the latitude and longitude. And when we try to, again, use sample regions for the region of interest, now the output value as a data frame will give you all the values that are overlaid with the NDVI layer. So let's try to see the data frame. So actually the data frame only contains 0, 0.0, and 0.3. So normally I gave 4 locations, but I only get 2 of them, which means I either did something wrong or these points are outside my region of interest. So actually, Utrecht and Leiden does not fall in this region of interest. So when it tries to overlay, the value returns to none, and this is not outputted in the data frame. That's why there is these points are missing on the output. If you want to do a proper overlay, you need to make sure that your region of interest covers all the sampling points. Otherwise, you get missing points like this. And finally, we can also try to plot the NDVI time series for these 4 points. Let's say that instead of just bounding with this region of interest, we can recall the Sentinel-2 collection, but without doing this filter bound in a specific region. And after that, you can do the exact same analysis without changing anything. We just only change the image collection output. So in this case, you can have any points because we have no strict geometric constraint in the overlay. And if you try to plot the time series, the NDVI time series for different points on Earth, you can get something like this. Apparently, the other 3 are definitely not in vegetated region, but point 2 is definitely and somewhere either forest or some grassland. Could be grassland, maybe a bit more, but probably forest. So we can access the tau time series for a point, again, using a simple sample region function. Of course, we are doing this for 4 points, but imagine you need to do this for 10,000 points or 100,000 points. So in this case, of course, it will be much more meaningful to do this sort of things. But also, you will see that easily. You may need to wait to get the analysis for, let's say, 10,000 point or 100,000 point. It will not be quite fast to overlay easily. Like in the final part, instead of GeoJSON, I wanted to give an example for the CSV as well. So now we are exporting this NDVI time series to the Google Earth Engine as CSV, not as GeoJSON. So if you go to your Google Drive, of course, again, like based on the speed you get, you will have in your recent file, when it's exported, you will receive a folder called Google Earth Engine Exports, which we already specified, this folder name, GE Exports. And inside, you will see that this CSV file is actually located. For example, in here, we can see that GeoJSON is already outputted. And also Amsterdam NDVI mean value. And soon you will also see the CSV file located in here, but there's a bit of a time lag, of course, between the time you ran the competition and the time the file is saved in here. It can actually changes a bit. So if the file is larger, of course, the time is also a bit large. So if you're downloading, let's say, Sentinel-2 files in a large scale, you may need to wait for hours. And if it also exceeds a certain number of pixels or a range, the Google Earth Engine will try to export the GeoTIFF by dividing it into chunks. So for one single GeoTIFF image, you may see 3 different chunks. So when you try to download them, you may need to re-mosaic them again. Otherwise, you will have, you can also have different weird shapes of Google GeoTIFF files in these chunks because they are not directly vertical in the coordinate system that you are playing with. So when you cut it, you may get a different weird shapes. So eventually you need some.
What's the chunk size?
Sorry?
What determines the chunk size now?
Google Earth Engine has this maximum file size limit to export. So if it exceeds some certain threshold, like 1.5 gigabyte or maybe 2, I don't know. So in that case, it divides into chunks so that it can easily.
Chunk size?
A chunk size is quite random. It's actually, yeah. For that, I don't have the proper information, but I think it depends on the type of the data, because in the background, Google Earth Engine stores all these GeoTIFFs as tiles. Also, there are some certain tile information also. So maybe it's if you're in the bound of 2 different tiles, it's dividing into different places for that tile. So the hands-on tutorial was like this. So is there any question?